Welcome to deep science sleep. Imagine yourself lying on a soft blanket in a meadow, far from the city lights. The grass beneath you releases its earthy scent into the cool evening air. Above you stretches an infinite canvas of darkness, punctuated by countless points of light. The Milky Way sweeps across the sky like a river of stars, and you feel yourself becoming part of something vast and ancient. Your breathing slows, your muscles relax. The weight of the day melts away as you gaze upward into the eternal night. Tonight, we're going to explore the most calming, peaceful facts about the night sky, each one designed to guide you gently towards sleep. Let the cosmos be your lullaby. The ancient history of stargazing. Long before cities glowed with artificial light, before screens illuminated our nights, humans looked up at the stars with wonder. This connection between humanity and the night sky stretches back not just centuries, but millennia, creating a continuous thread that links us to our most distant ancestors. When you look at the stars tonight, you're participating in perhaps the oldest human activity, one that has brought peace and perspective to countless souls throughout history. The earliest stargazers left us clues about their observations. Deep in the caves of southwestern France, 17,000 years ago, prehistoric artists painted animals on cave walls, and interspersed among these creatures, researchers believe they also painted the stars. The Lascaux caves contain what may be astronomical imagery, depicting constellations visible at the time of their creation. Imagine those ancient people, seeking shelter in those caves, looking up through the entrance at the same stars we see today, finding patterns in the darkness, creating meaning from the eternal lights above. 6,000 years ago in ancient Mesopotamia, in the fertile land between the Tigris and Euphrates rivers, the Babylonians erected watchtowers specifically to scan the night sky. These early astronomers were meticulous, mapping the stars and visible planets with remarkable precision, recording their observations on clay tablets that have survived to this day. They created the first calendars based on celestial movements, using the predictable dance of heavenly bodies to organize agricultural cycles and religious ceremonies. Dating back to around 1800 years before the Common Era, the Babylonians were among the first civilizations to document the movements of the sun and moon, maintaining extraordinarily detailed records of daily, monthly, and yearly positions of celestial bodies. The night sky was their clock, their calendar, and their connection to the divine. When a Babylonian priest looked up at night, studying the slow procession of planets across the background of fixed stars, they were engaging in an act of devotion and science simultaneously. The same stars that guided their planting seasons also spoke to them of cosmic order and meaning. The zodiac system we still recognize today has its roots in these ancient Babylonian observations, a legacy that has persisted for over 4,000 years. In ancient Egypt, astronomy was woven into the very fabric of civilization. The Egyptians didn't just observe the stars for mystical purposes. They used them practically to predict the annual flooding of the Nile River, the lifeblood of their civilization. The Great Pyramid of Giza, one of humanity's most enduring monuments, was built with astronomical precision. Its sides align almost perfectly with the cardinal directions, and it was constructed to align with the North Star, though not with Polaris as we know it today. Due to the slow wobble of Earth's axis, a phenomenon called precession, The North Star in ancient Egyptian times was Thuban, a faint star in the constellation Draco. Picture the construction of that pyramid, workers laboring under the desert sun. But at night, astronomers carefully observing Thuban's position, ensuring that this massive stone structure would point toward the heavens with perfect accuracy. The Nabta Playa in southern Egypt contains a circular stone structure, presumed to be a giant calendar designed to identify the summer solstice. This megalithic site predates Stonehenge by at least 1,000 years, demonstrating that the drive to mark and measure the movements of celestial bodies is deeply rooted in human nature. Across the world in ancient China, astronomers compiled some of the most detailed astronomical records ever created. Gan De, one of China's most notable ancient astronomers, was the first person to notice what he described as a small reddish star around Jupiter. Modern astronomers now believe he was observing Ganymede, one of Jupiter's largest moons, with nothing but his naked eyes. This observation occurred more than 2,000 years before Galileo would use his telescope to officially discover Jupiter's moons. Shi Xin created one of the most detailed and oldest catalogs of stars, the Star Catalog of Shi, an achievement that helped establish the foundations of celestial mapping. The Chinese also took notice of stars that suddenly appeared among the fixed stars, phenomena we now understand to be supernovae, stellar explosions so bright they can briefly outshine entire galaxies. The Dunhuang Star Atlas, discovered by an archaeologist in a Buddhist cave in Dunhuang, China, is the earliest known preserved star map in the world, dating back before the year 700 of the Common Era. Think about the patience required to create these star maps. Night after night, year after year, generations of observers noting the positions of stars, tracking their movements, recognizing patterns. There were no electric lights to compete with the stars, no distractions from screens or devices, just the observer, the darkness, and the infinite field of stars above. In ancient Greece, astronomy transformed from an observational practice into a mathematical and philosophical endeavor. Greek scholars like Eratosthenes didn't just look at the stars, they measured the Earth itself using the stars as reference points. Around 240 years before the Common Era, Eratosthenes calculated the circumference of the Earth using shadows and geometry, arriving at a figure that was remarkably close to the actual value, off by only a few hundred or a few thousand miles depending on which ancient measurement unit he used. Hipparchus, another Greek astronomer working in the 2nd century before the Common Era, compiled the first stellar catalog, listing the positions of 850 stars across the sky with a precision of about 1 degree. He achieved this using only naked-eye observations and simple instruments like gnomons, astrolabes, and armillary spheres. He also created the magnitude system for describing star brightness, a system still in use today with only minor modifications. When you hear that a star has a magnitude of 2 or 4, you're using a system that a Greek astronomer invented over 2,000 years ago. Hipparchus also discovered the precession of the equinoxes, the slow wobble in Earth's axis that causes the positions of stars to shift gradually over thousands of years. This wobble takes about 26,000 years to complete one full cycle, which means the North Star slowly changes over time. The patience required to notice such a gradual shift speaks to the dedication of these ancient astronomers, who compared observations across generations to detect patterns that unfolded over timescales far longer than a human lifetime. In the Mayan civilization of Mesoamerica, astronomy reached sophisticated heights. The Mayans built elaborate observatories like El Caracol at Chichen Itza, architecturally aligned with the movements of the Sun, Moon, Venus, and other planets. Their astronomical observations were recorded in codices, folding books written on bark paper. They developed complex calendar systems that interwove a 260-day ritual calendar called the Tzolk'in with a 365-day solar calendar called the Hab, creating a calendar round that repeated every 52 years. For recording historical dates and prophetic events, they used the long count calendar, a system so precise that it rivals modern calendars in accuracy. The heliacal rising of the Pleiades star cluster, when these stars became visible just before sunrise, marked the start of the agricultural year for the Maya. Imagine farmers watching the eastern horizon before dawn, waiting for that cluster of stars to appear, knowing that their emergence signaled the time to plant crops. The stars weren't just beautiful, they were essential guides for survival. On remote Pacific islands, Polynesian navigators developed an intimate relationship with the night sky that allowed them to travel thousands of miles across open ocean without instruments. They memorized the positions of stars, the patterns of their rising and setting, using this knowledge to navigate from island to island across vast stretches of empty sea. The night sky was their map, each constellation a waypoint on journeys that seem impossible without modern technology. When a Polynesian navigator set out across the Pacific, they carried no compass, no GPS, just an encyclopedic knowledge of the stars and an understanding of how those stars moved throughout the night and across the seasons. These ancient astronomers, from Babylon to Greece, from Egypt to China, from the Maya to the Polynesians, all shared one thing. They looked up at the same stars we see today. The stars have barely moved in the time since those ancient observations. When you see Sirius, the brightest star in our night sky, you're seeing the same star that guided Egyptian priests, that Polynesian navigators used to cross oceans, that Chinese astronomers recorded in their detailed catalogs. This continuity, this connection across time, is one of the most peaceful aspects of stargazing. The night sky is eternal, a constant presence that has witnessed all of human history and will continue long after we're gone. The physics of starlight and what we see. Every point of light you see in the night sky has traveled an enormous distance to reach your eyes. The light from stars isn't just illumination, it's information, messages sent across the vast emptiness of space, carrying with them stories about the nature and life of distant suns. Understanding what starlight really is and how it comes to be adds a dimension of wonder to the simple act of looking up. Stars shine because of nuclear fusion, a process so powerful and so fundamental that it literally creates the elements that make up everything around us, including our own bodies. Deep in the core of a star, conditions are extreme. Temperatures exceed 15 million degrees Celsius. The pressure is so intense that it would crush anything we know instantly into oblivion. In this environment, hydrogen atoms, the simplest and most abundant element in the universe, are stripped of their electrons, creating a plasma of bare protons and free electrons. These protons naturally repel each other because they both carry positive electrical charges, and like charges push apart. According to classical physics, they should never be able to get close enough to merge. But quantum mechanics reveals a beautiful loophole in the laws of physics, a phenomenon called quantum tunneling. Because particles at this scale don't behave like solid objects but rather like waves with probabilities, there's a small but significant chance that protons can tunnel through the energy barrier that separates them and suddenly find themselves close enough for the strong nuclear force to take over. When this happens, the protons fuse together. Through a series of reactions called the proton-proton chain, four hydrogen nuclei eventually combine to form one helium nucleus. But here's the magical part. The helium nucleus weighs slightly less than the 4 hydrogen nuclei that went into making it. About 0.7% of the mass disappears. Where did it go? It was converted into pure energy, in accordance with Einstein's most famous equation, E equals mc squared. That missing mass, converted into energy, is what makes stars shine. Every second, the sun converts approximately 4 million tons of matter into pure energy through this process. 4 million tons of matter simply ceasing to exist as matter and becoming light and heat instead. This has been happening continuously for about 4.5 billion years, and the sun has enough hydrogen fuel to continue for about another 5 billion years before it begins to die. That energy, born in the crushing pressure and searing heat of the solar core, begins a long journey outward. It doesn't travel straight out. Instead, photons, particles of light, bounce around inside the star, absorbed and re-emitted by atoms countless times. This random walk through the dense stellar interior takes anywhere from 10,000 to 170,000 years, depending on whose calculations you trust. The photon that strikes your eye today, causing you to see the sun, was created in the solar core before human civilization existed, before we built cities or invented writing, before we even started farming. Once that photon finally reaches the surface of the star, it escapes into space and travels in a straight line at the speed of light. From the sun to Earth takes only 8 minutes and 20 seconds. So when you look at the sun, you're seeing it as it was 8 minutes ago. The light from the next nearest star, Proxima Centauri, takes 4.2 years to reach us. The light from more distant stars can take hundreds, thousands, or even millions of years to complete its journey. This means that when you look at the night sky, you're literally looking back in time. You're not seeing the stars as they are now, but as they were when their light began its journey to your eyes. Some of the stars you see may have already died, their light still traveling across the galaxy, unaware that its source no longer exists. This creates a strange, peaceful kind of timelessness to stargazing. You're witnessing ancient history, cosmic messages from the past, all arriving at your eyes in the present moment. The color of a star tells you about its temperature. Hot stars burn blue or white, while cooler stars glow red or orange. Our sun, a medium-temperature star, shines yellow-white. The hottest stars, classified as O-type or B-type on the spectral scale, burn at temperatures exceeding 30,000 degrees Celsius on their surfaces and appear brilliant blue. These stars are massive, short-lived, and extraordinarily luminous. A single O-type star can be 1,000,000 times brighter than our sun. Cooler stars, the red dwarfs and red giants, have surface temperatures of only 3,000 to 4,000 degrees Celsius. Red is the coolest color for a star, just as it's the coolest flame in a fire. These red stars can be enormous in size, like the red supergiant Betelgeuse in the constellation Orion, or they can be tiny and dim, like the countless red dwarf stars that make up the majority of stars in the galaxy but are too faint for us to see with the naked eye. Between these extremes lie stars like our sun, and stars slightly hotter or cooler, creating a rainbow of stellar colors. If you look carefully at bright stars on a clear night, you can often perceive these color differences. Betelgeuse has a distinctly reddish tint. Rigel, also in Orion, glows blue-white. Sirius is brilliant white with just a hint of blue. These colors aren't just beautiful. They're information, silent messages about the nature of these distant suns. Stars also twinkle, a phenomenon that has nothing to do with the stars themselves and everything to do with our atmosphere. As starlight passes through layers of air with different temperatures and densities, it gets bent and refracted, causing the star's apparent position and brightness to fluctuate rapidly. This scintillation creates that characteristic twinkling effect. Planets, being closer and appearing as tiny disks rather than points in powerful telescopes, show less twinkling because their light comes from a slightly wider area in the sky. On very still, clear nights, when the air is calm and transparent, stars twinkle less. Their light reaches your eyes more steadily. This is why professional observatories are built on high mountains in remote locations where the air is thin, dry, and stable. The best conditions for astronomical observation often coincide with the most beautiful stargazing experiences for casual observers as well. The light from stars carries within it the entire electromagnetic spectrum. What we see with our eyes is just a tiny fraction of the radiation stars emit. They also produce infrared light, ultraviolet light, X-rays, and radio waves. Our sun floods the solar system with all these forms of energy, but Earth's atmosphere protects us from most of the harmful high-energy radiation while allowing visible light and some infrared through. This selective filtering makes life possible while still letting us see the beauty of the sky. When you see a star, you're witnessing the endpoint of an extraordinary process. Hydrogen atoms, forged in the first moments after the Big Bang, compressed by gravity into dense balls, crushed until they undergo fusion. Their mass converted to energy, that energy embarking on a journey of thousands of years through the star's interior, finally emerging as light, crossing vast distances of space, passing through our atmosphere, and landing on the retina of your eye where it triggers a chemical reaction that sends an electrical signal to your brain, creating the experience of seeing starlight. This entire chain, from fusion to perception, connects you directly to the most fundamental processes in the universe. You are made of atoms that were once forged in stars, atoms that were scattered into space when ancient stars died, atoms that condensed into new clouds of gas and dust, eventually forming our solar system, our planet, and you. You are literally made of stardust, and when you look at stars, you're looking at factories that are still producing the same elements that compose your body. The moon, our constant celestial companion. Among all the objects in the night sky, the moon holds a special place in human consciousness. It's the only celestial body close enough to show clear surface features to the naked eye, the only one humans have walked upon, and the only one that dramatically changes its appearance throughout the month. The moon has been our companion throughout all of human history, a constant presence that has inspired countless stories, poems, and songs. The moon orbits Earth at an average distance of about 384,000 kilometers, or roughly 239,000 miles. This distance varies because the moon's orbit isn't a perfect circle but rather an ellipse. At its closest approach, called perigee, the moon comes within 356,400 kilometers of Earth. At its farthest point, apogee, it recedes to 406,700 kilometers away. This variation in distance causes the moon's apparent size to change by up to 14% and its brightness to vary by up to 30%. When the moon is at perigee during a full moon, we get what's popularly called a supermoon, when our satellite appears noticeably larger and brighter than usual. The difference is subtle but real, and if you've ever looked at a supermoon and felt that it seemed unusually magnificent, your intuition was correct. The moon really was closer. Its face really did span a larger portion of the sky. The moon completes one orbit around Earth approximately every 27.3 days. This is called the sidereal month because it's measured against the background of fixed stars. However, because Earth is also moving in its orbit around the Sun during this time, the moon needs to travel a bit further to reach the same phase, which is why the cycle of phases from new moon to new moon takes 29.5 days. This is called the synodic month. The phases of the moon are perhaps its most noticeable feature. New moon occurs when the moon lies between Earth and the Sun, with its illuminated side facing away from us, rendering it invisible in the glare of sunlight. As the moon moves in its orbit, we begin to see a thin crescent of illuminated surface, growing larger each night. This is the waxing crescent phase. When exactly half the moon's face is illuminated, we have first quarter. The moon continues to grow, becoming a waxing gibbous moon, until finally, when Earth lies between the moon and Sun, we see the full moon, with its entire face illuminated by sunlight. After the full moon, the process reverses. The moon becomes a waning gibbous, then third quarter, then a waning crescent, finally disappearing again at new moon. This cycle has repeated billions of times since the moon formed, a rhythm as reliable as the beating of a cosmic heart. One of the most intriguing aspects of the moon is that it always shows us the same face. This phenomenon, called tidal locking, occurs because the moon's rotation period exactly matches its orbital period. It takes the moon 27.3 days to rotate once on its axis, which is exactly how long it takes to orbit Earth once. This synchronization means that one lunar day, from sunrise to sunset on the moon, lasts about 29.5 Earth days. Tidal locking isn't a coincidence, but rather the result of gravitational interactions between Earth and the moon over billions of years. In the distant past, the moon rotated faster than it does now, showing all sides to Earth as it orbited. But Earth's gravity created tidal bulges in the moon's slightly deformable body, and these bulges acted like brakes, gradually slowing the moon's rotation. Eventually, the moon's rotation slowed enough that one side became permanently locked facing Earth. The side of the moon we see is called the near side, while the opposite hemisphere is the far side. The far side is often incorrectly called the dark side, but this is a misnomer. The far side receives just as much sunlight as the near side. It's just that we never see it from Earth. When we experience a new moon, the far side is actually in full daylight, while the near side facing us is in darkness. Interestingly, during the lunar night on the near side, when the sun isn't illuminating it, the surface isn't completely dark. Earth acts like a giant mirror, reflecting sunlight onto the moon's surface in a phenomenon called earthshine. This reflected light is strong enough that lunar surface features can be observed from Earth even when the sun isn't directly lighting them. From the moon, Earthshine makes the night sky about 43 times brighter, sometimes even 55 times brighter, than a moonlit night on Earth. The moon doesn't just orbit Earth, it's also gradually moving away from us. Laser reflectors placed on the lunar surface by Apollo astronauts have allowed scientists to measure this recession with extreme precision. The moon is drifting away at about 3.8 centimeters, roughly 1.5 inches per year. This happens because of the same tidal forces that locked the moon's rotation. Earth's rotation is gradually slowing down due to tidal interactions with the moon, and the angular momentum lost by Earth is transferred to the moon, causing it to move into a higher orbit. This means that in the distant past, the moon was much closer to Earth. When it first formed, likely from debris created when a Mars-sized object collided with the early Earth about 4.5 billion years ago, the moon orbited much nearer, appearing enormous in the sky. At that time, Earth's day was only about 5 hours long because our planet rotated faster. The moon's gravity has been gradually slowing Earth's rotation while moving itself farther away, a slow dance that has continued for billions of years. In about 500 million to 1 billion years, the moon will have moved far enough away that total solar eclipses will no longer be possible. Right now, we live in a special time when the moon and sun appear almost exactly the same size in our sky, about half a degree across, allowing the moon to perfectly cover the sun during a total eclipse. This perfect alignment is an extraordinary coincidence, with no deep physical reason for it. The sun is about 400 times farther from Earth than the moon, but it's also about 400 times larger, making them appear the same size from our perspective. This coincidence has allowed humans to study the sun's outer atmosphere, the corona, during total solar eclipses. When the moon blocks the brilliant photosphere, the faint corona becomes visible, revealing structures and phenomena that would otherwise be impossible to see from Earth. Ancient civilizations who witnessed total solar eclipses often interpreted them as omens or supernatural events. Even today, with our scientific understanding, witnessing the day turn to night as the moon's shadow sweeps across the landscape remains one of the most awe-inspiring experiences in nature. The moon's gravitational influence on Earth creates ocean tides, the rhythmic rise and fall of sea level that occurs twice daily. The moon's gravity pulls more strongly on the water closest to it, creating a bulge on the moon-facing side of Earth. Simultaneously, on the opposite side of Earth, another bulge forms because that water is farther from the moon and experiences less gravitational pull. As Earth rotates beneath these two bulges, any given location on the coast experiences 2 high tides and 2 low tides each day. The sun also contributes to tides, though its effect is smaller than the moon's despite its greater mass, because tidal force depends on the difference in gravitational pull across Earth's diameter, and the sun is much farther away. When the sun and moon align at new moon or full moon, their tidal effects add together, creating especially high and low tides called spring tides. When they're at right angles during quarter moons, their effects partially cancel, creating more moderate tides called neap tides. Looking at the moon through even a small telescope reveals a world of detail. The dark areas visible to the naked eye, once thought to be seas and thus called Maria, Latin for seas, are actually vast plains of solidified lava from ancient volcanic eruptions. The lighter areas are heavily cratered highlands, the moon's original crust, battered by billions of years of meteorite impacts. Some craters are large enough to see with the naked eye under good conditions. Tycho, in the southern highlands, is a relatively young crater surrounded by bright rays of ejected material that stretch across the moon's surface. The boundary between the illuminated and dark portions of the moon, called the terminator, is where surface features cast dramatic shadows. Looking at the moon when it's a crescent or quarter phase, rather than full, reveals far more detail because the shadows emphasize topography. Mountains, crater rims, and the edges of Maria stand out in sharp relief along the terminator. Walking on the moon must have been a surreal experience for the Apollo astronauts. The lunar surface is covered in a fine gray dust called regolith, created by billions of years of meteorite bombardment pulverizing the rocks. There's no air, so sounds don't carry, making the environment utterly silent except for mechanical sounds transmitted through the astronaut suits. The sky is always black, even during the lunar day, because there's no atmosphere to scatter sunlight. Earth hangs in that black sky, appearing about 4 times larger than the moon appears from Earth, going through phases just like the moon does from our perspective, but moving much more slowly because the moon rotates so slowly. The moon's daytime surface temperature can reach 127 degrees Celsius in direct sunlight, while nighttime temperatures plunge to minus 173 degrees Celsius. These extreme temperature swings occur because there's no atmosphere to distribute heat or provide insulation. The lunar environment is harsh and unforgiving, yet also hauntingly beautiful in its stark simplicity. Despite its airless, waterless nature, recent discoveries have found water ice in permanently shadowed craters near the moon's poles. These regions never receive direct sunlight and have maintained temperatures cold enough to trap water for billions of years. This ice could potentially be used by future lunar bases, providing drinking water and oxygen, and even rocket fuel through electrolysis. The moon continues to be our closest celestial companion, a world we've walked upon yet still don't fully understand. It stabilizes Earth's axial tilt, which helps maintain our climate stability. Without the moon, Earth's axis would wobble more dramatically over time, causing wild climate swings that might have prevented complex life from evolving. In a very real sense, the moon has been essential to making Earth a stable, habitable world. Planets in our night sky, while stars remain fixed in their positions relative to each other night after night, there are several bright objects that wander across the sky, slowly changing their positions among the constellations. The ancient Greeks called these objects planets, meaning wanderers, and we still call them planets today. These worlds of our solar system, shining not by their own light, but by reflecting sunlight, have captivated observers throughout human history. 5 planets are easily visible to the naked eye: Mercury, Venus, Mars, Jupiter, and Saturn. These are the planets ancient astronomers knew about, the wandering stars that moved through the zodiac constellations, while the true stars maintained their eternal patterns. Each planet has its own character, its own color, its own rhythm of appearance and disappearance. Mercury is the smallest planet and the one closest to the Sun, making it challenging to observe. It never ventures far from the Sun in the sky, appearing either shortly after sunset or shortly before sunrise. For most of the year, Mercury is lost in the Sun's glare, but a few times annually, it reaches its greatest separation from the Sun, called greatest elongation, becoming visible as a bright star-like point low on the horizon. Catching sight of Mercury requires clear skies, a good view of the horizon, and knowing exactly when and where to look. Because of these challenges, some amateur astronomers never see Mercury despite years of stargazing, while others make a special effort to spot it whenever possible. Venus, by contrast, is impossible to miss when it's visible. Often called the morning star or evening star, Venus is the third brightest natural object in the sky after the Sun and Moon. It can become bright enough to cast faint shadows and is occasionally visible in full daylight if you know exactly where to look. Venus shines so brilliantly because of its thick atmosphere of carbon dioxide clouds that reflect about 75% of the sunlight striking them, and because it comes closer to Earth than any other planet, approaching within 40 million kilometers at inferior conjunction. Like Mercury, Venus appears only in the morning or evening sky, never overhead at midnight, because its orbit lies between Earth and the Sun. When Venus appears in the evening, it's often the first star-like object visible after sunset, hanging brilliantly in the western twilight. When it appears in the morning, it's the last to fade as dawn brightens the eastern sky. Through a telescope, Venus shows phases like the Moon, waxing and waning as it orbits the Sun, a phenomenon that helped prove the heliocentric model of the solar system. Mars captures imagination like no other planet. Its reddish color, caused by iron oxide rust covering its surface, has led to associations with blood, war, and the god of war in many cultures. Mars varies dramatically in brightness depending on its position relative to Earth. At its closest approach during favorable oppositions, when Earth passes between Mars and the Sun, Mars can become brighter than Jupiter, glowing like an orange-red ember in the night sky. At its farthest and dimmest, it can be difficult to distinguish from background stars. This variation occurs because Earth and Mars orbit the Sun at different speeds and distances. Earth, being closer to the Sun, completes its orbit faster, periodically overtaking Mars like the inside runner on a track. Every 26 months, Earth and Mars come into opposition, with Mars appearing at its biggest and brightest. But because both orbits are elliptical rather than circular, not all oppositions are equal. When opposition occurs with Mars near perihelion, its closest approach to the Sun, it comes especially close to Earth, creating what's called a favorable or perihelic opposition. The opposition of 2003 was particularly spectacular, bringing Mars closer to Earth than it had been in nearly 60,000 years. Through a telescope, Mars reveals subtle surface features. Dark regions once thought to be vegetation or seas, bright polar ice caps that grow and shrink with the Martian seasons, and occasionally, dust storms that can envelope the entire planet. The thin Martian atmosphere sometimes produces clouds, and careful observers can even detect the planet's rotation by watching surface features shift over a few hours. Jupiter is the king of planets, a gas giant so massive that it contains more than twice the mass of all other planets combined. Despite its enormous distance, ranging from about 600 to nearly 960 million kilometers from Earth, depending on positions in orbits, Jupiter shines brilliantly in our night sky, usually second only to Venus among the planets. Its brightness comes from its huge size, which gives it a large surface area to reflect sunlight, and from its highly reflective cloud tops. Through binoculars or a small telescope, Jupiter reveals 4 bright moons discovered by Galileo in 1610: Io, Europa, Ganymede, and Callisto. These Galilean moons, as they're now called, orbit Jupiter quickly, changing their positions noticeably from night to night, sometimes even hour to hour. You can watch them pass in front of Jupiter, casting shadows on its cloud tops, or disappear behind the planet, or pass through Jupiter's shadow, being eclipsed. No 2 nights show the same arrangement of moons, providing endless variation for observers. With a larger telescope, Jupiter's parallel cloud bands become visible, stretching across its rapidly rotating face. Jupiter rotates faster than any other planet, completing 1 rotation in less than 10 hours. This rapid spin stretches its clouds into distinct zones and belts, light and dark bands that circle the planet parallel to its equator. The most famous feature is the Great Red Spot, an enormous storm larger than Earth that has persisted for at least several centuries, possibly much longer. This storm, a high-pressure anticyclone, rotates counterclockwise with winds exceeding 400 kilometers per hour. Saturn is perhaps the most beautiful planet, famous for its stunning ring system. Even through a small telescope, the rings are visible as distinct structures extending on either side of the planet's golden globe. These rings aren't solid but consist of countless billions of particles, ranging from dust grains to house-sized chunks, all orbiting Saturn in a thin disk. The particles are primarily water ice mixed with some rocky material, making the rings highly reflective. The rings appear different depending on Saturn's position in its orbit. Because Saturn's axis is tilted, we view the rings from different angles as the planet moves around the Sun. Every 15 years or so, Earth crosses the plane of Saturn's rings, causing them to appear edge-on and nearly disappear, since they're only about 10 to 30 meters thick. At other times, the rings are tilted toward or away from us, presenting their full glory. Through a telescope, Saturn's rings show subtle divisions. The most prominent is the Cassini division, a dark gap visible even in small telescopes, separating the bright inner ring from the outer ring. This division is maintained by gravitational resonances with Saturn's moons, particularly Mimas. The ring system extends outward from the planet for over 280,000 kilometers, yet it's so thin relative to its diameter that if you made a scale model with rings the size of a football field, the rings would be about as thick as tissue paper. Saturn also has a family of moons, the largest being Titan, which is bigger than the planet Mercury. Titan has a thick nitrogen atmosphere and methane lakes on its surface, making it one of the most fascinating worlds in the solar system. Through large amateur telescopes, several of Saturn's brighter moons can be seen as tiny points of light near the planet. The outer planets, Uranus and Neptune, are too faint to have been known to ancient astronomers. Uranus was discovered by William Herschel in 1781 during a systematic survey of the sky. It's just barely visible to the naked eye under excellent conditions, appearing as a very faint star, but a telescope reveals its tiny greenish disk. Neptune, discovered in 1846, is too faint for naked eye visibility but can be seen through binoculars if you know exactly where to point. When planets appear together in the sky, the results can be spectacular. Venus and Jupiter passing close together create a brilliant pairing that has been called the Star of Bethlehem by some scholars. suggesting that the conjunction of these planets might explain the biblical story. When three or more planets gather in one part of the sky, called a planetary conjunction or massing, the sight draws people outside to look up and marvel. Planets move slowly against the background stars, following the path of the ecliptic, the plane of the solar system projected onto the celestial sphere. Over weeks and months, you can watch them shift eastward among the constellations, each moving at its own pace. Mercury races around the Sun in 88 days. Venus takes 224 days. Mars requires about 687 days, nearly 2 Earth years. Jupiter takes 12 years to complete its journey through the zodiac, while Saturn requires about 29 years. This means that Jupiter moves through roughly one constellation per year, a leisurely pace that allows for prolonged observation. Saturn moves even more slowly, spending about 2.5 years in each zodiacal constellation. Ancient astrologers paid careful attention to these movements, noting when planets entered different constellations, when they aligned with bright stars, when multiple planets appeared together. While we now understand the physical reality behind these movements, the visual spectacle remains just as compelling as it was thousands of years ago. Occasionally, planets appear to move backward through the sky, an apparent motion called retrograde. This happens because we're observing from a moving platform, Earth, which is itself orbiting the Sun. When Earth overtakes a slower-moving outer planet like Mars, Jupiter, or Saturn, that planet appears to slow down, stop, move backward for a period of time, stop again, and then resume its normal eastward motion. This retrograde motion confused ancient astronomers who believed Earth was stationary at the center of the universe, leading to increasingly complex models with epicycles and deference to explain the observed motions. The heliocentric model explained retrograde motion simply and elegantly as a perspective effect. Watching planets over time connects you to the rhythm of the solar system. You become aware of the cosmic clockwork, the predictable dance of worlds around the Sun. There's something deeply peaceful about this predictability, knowing that the planets will continue their orbits, that Jupiter will return to the same part of the sky in 12 years, that Saturn will complete its majestic circuit in 29 years, that Venus will appear and disappear and appear again with reliable regularity. In a world of constant change and uncertainty, the planets remind us that some things remain constant, governed by the same gravity that has orchestrated their motions for billions of years. Deep space objects, nebulae, galaxies, and clusters. Beyond the planets lie objects of staggering scale and beauty. Nebulae, star clusters, and entire galaxies. These deep space objects challenge comprehension, representing distances so vast and structures so enormous that they seem almost impossible. Yet on dark, clear nights, many of them are visible to the naked eye, their ancient light finally completing journeys that began long before humans existed. Star clusters are among the most accessible deep space objects. They're groups of stars born together from the same cloud of gas and dust, bound together by mutual gravity. Open clusters are loose associations of dozens to thousands of young stars, still near their birthplace, slowly drifting apart over millions of years. Globular clusters are tight spherical collections of hundreds of thousands or even millions of ancient stars, orbiting in the halo around galaxies. The Pleiades, also called the Seven Sisters, is perhaps the most famous open cluster. Located in the constellation Taurus, it's visible to the naked eye as a small, fuzzy patch of light. Most people can distinguish 6 or 7 individual stars without optical aid, though exceptionally sharp-sighted individuals have reported seeing up to 14. Through binoculars, the Pleiades transforms into a jewel box of dozens of brilliant blue-white stars, all extremely young by stellar standards, having formed only about 100 million years ago. The stars of the Pleiades are hot and massive, burning through their nuclear fuel at prodigious rates. They won't live as long as our Sun, exhausting their hydrogen in mere hundreds of millions of years rather than billions. But right now, they're in their prime, shining brilliantly against the darkness. The cluster is surrounded by faint reflection nebulosity, dust that reflects the blue light from the hot stars, visible in long-exposure photographs though barely perceptible visually even in large telescopes. The Hyades, another prominent cluster in Taurus, forms the V-shaped face of the celestial bull. These stars are older than the Pleiades, about 650 million years old, and they're much closer to us, only about 150 light-years away compared to the Pleiades' 440 light-years. The bright orange star Aldebaran appears to be part of the Hyades, but is actually a foreground star less than half the distance, merely appearing in the same direction by coincidence. Globular clusters present a different spectacle entirely. These ancient stellar cities orbit far above and below the galactic disk, relics from the early universe. The stars in globular clusters are typically 10 to 12 billion years old, formed when the universe itself was young. Omega Centauri, the largest globular cluster visible from Earth, contains about 10 million stars packed into a sphere about 150 light-years across. From the middle of such a cluster, the night sky would be spectacular beyond imagination, with thousands of stars brighter than Venus scattered across the heavens, providing enough light to read by even on moonless nights. From our perspective, globular clusters appear as fuzzy, concentrated glows through binoculars, resolving into countless individual stars through larger telescopes. The visual effect resembles spilled salt or sugar, a dense concentration of pinpoint lights gradually thinning toward the edges. The cores are so densely packed that individual stars can't be distinguished even in large amateur telescopes, blending into a continuous glow. Nebulae, clouds of gas and dust in space, come in several varieties, each beautiful in its own way. Emission nebulae glow with their own light, energized by hot young stars embedded within them. The Orion Nebula, located in the Sword of Orion, is the nearest massive star-forming region to Earth, about 1,340 light-years away. It's visible to the naked eye as a fuzzy patch, the middle star in Orion's sword, but through telescopes, it reveals extraordinary detail and structure. The Orion Nebula is a stellar nursery where new stars are currently being born. The gas glows red from hydrogen emission, though our eyes are not sensitive enough to see the color, perceiving instead a greenish-gray glow. Photographs reveal swirls and tendrils of glowing gas, dark lanes of dust, and young stars emerging from their cocoons of gas. The trapezium, a group of 4 bright young stars near the nebula's center, provides the energy that makes the entire cloud glow. These stars are only about 1 million years old, infants by stellar standards. Looking at the Orion Nebula, you're witnessing the process that created our Sun and solar system 4.5 billion years ago. Inside clouds like this, gravity pulls gas and dust together into dense clumps. As these clumps contract, they heat up, eventually becoming hot enough to ignite nuclear fusion, birthing new stars. Some of the stars forming in the Orion Nebula right now will eventually develop planetary systems, and perhaps billions of years from now, beings on planets orbiting those stars will look out at their own night sky, seeing different constellations, different nebulae, different galaxies. Planetary nebulae, despite their name, have nothing to do with planets. They're shells of gas ejected by dying stars, illuminated by the extremely hot stellar core left behind. The Ring Nebula in Lyra is the classic example, appearing through telescopes as a perfect ring or donut of glowing gas. This ring is actually a spherical shell that we're viewing from the side, our perspective making it appear ring-shaped. The central star, now a white dwarf, shines with a surface temperature of over 100,000 degrees Celsius, its ultraviolet light causing the expanding gas shell to fluoresce. In about 5 billion years, our Sun will create a similar planetary nebula. As it exhausts its hydrogen fuel, it will swell into a red giant, eventually ejecting its outer layers into space, while its core collapses into a white dwarf. The expanding shell of gas will glow for a few tens of thousands of years, gradually dispersing into the interstellar medium, contributing material that may someday form new stars and planets. Supernova remnants are the debris from exploded stars, expanding shock waves of gas plowing through the interstellar medium. The Crab Nebula, result of a supernova explosion witnessed and recorded by Chinese and Arab astronomers in 1054 of the Common Era, is still expanding today, its filaments moving outward at speeds of 1,500 kilometers per second. At the center of the crab lies a pulsar, a rapidly spinning neutron star, the crushed core of the exploded star, rotating 30 times per second and beaming radiation into space like a cosmic lighthouse. The Veil Nebula, a much older supernova remnant in Cygnus, stretches across a large area of sky, its delicate filaments tracing the expanding shock wave from a star that exploded thousands of years ago. These remnants are where heavy elements created in stellar cores return to space, enriching the interstellar medium with carbon, oxygen, iron, and other elements essential for planets and life. Galaxies represent the ultimate in deep space objects. Entire star cities, each containing billions or trillions of stars, separated from us by millions or billions of light years. The Andromeda Galaxy, our nearest large galactic neighbor, lies 2.5 million light years away. The light you see when observing Andromeda left that galaxy 2.5 million years ago, when our Australopithecine ancestors were just beginning to walk upright in Africa. Despite this immense distance, Andromeda is visible to the naked eye under good conditions, appearing as a faint, elongated smudge in the constellation Andromeda. Through binoculars, it reveals more structure, showing its oval shape and bright central core. Through telescopes, the outer spiral arms begin to appear, though photographing Andromeda reveals far more detail than visual observation. The galaxy spans about 3 degrees of sky, 6 times the width of the full moon, though only the bright central regions are visible to most observers. Andromeda contains approximately 1 trillion stars, about twice as many as our Milky Way. It's moving toward us at about 110 kilometers per second, and in about 4.5 billion years, it will collide with the Milky Way. This galactic merger will fundamentally reshape both galaxies, eventually creating a single giant elliptical galaxy. The Sun and Solar System will likely survive this collision unharmed, since stars are so far apart that direct collisions are virtually impossible. But our night sky will transform beyond recognition as the two galaxies interpenetrate and merge. The Triangulum Galaxy, third largest member of our local group of galaxies, is another naked-eye object under pristine dark skies, though it's quite challenging to see, requiring excellent conditions and keen eyesight. It lies about 3 million light-years away and contains about 40 billion stars. The light reaching your eyes from Triangulum began its journey before Homo erectus evolved. In the southern hemisphere, the large and small Magellanic Clouds are prominent features of the night sky, appearing like detached pieces of the Milky Way. These are dwarf satellite galaxies orbiting the Milky Way, much smaller than our galaxy but still containing billions of stars. The Large Magellanic Cloud lies about 160,000 light-years away, while the Small Magellanic Cloud is about 200,000 light-years distant. These irregular galaxies are gradually being pulled apart by the Milky Way's gravity, leaving trails of gas and stars in their orbits. Observing galaxies reminds us of the scale of the universe. Each one of those faint smudges of light is an entire galaxy, a system containing hundreds of billions or trillions of stars, many of which likely have planets, spread across hundreds of thousands of light-years. And there are hundreds of billions of galaxies in the observable universe, perhaps 2 trillion of them, each a city of stars, each potentially harboring worlds beyond counting. The famous Hubble Deep Field image, taken by pointing the Hubble Space Telescope at a seemingly empty patch of sky no bigger than a grain of sand held at arm's length, revealed about 3,000 galaxies in that tiny area. Extrapolating this across the entire sky suggests there are more galaxies in the universe than there are stars in the Milky Way. The universe is almost inconceivably vast, and we're just beginning to explore and understand its grandeur. The Milky Way and our place in the cosmos. On truly dark nights, far from city lights, a luminous band stretches across the sky, a river of faint light flowing from horizon to horizon. This is the Milky Way, our home galaxy seen from within, the combined light of hundreds of billions of distant stars too faint to distinguish individually. Observing the Milky Way is one of the most profound experiences nature offers, connecting you viscerally to the cosmic structure we inhabit. The Milky Way is a barred spiral galaxy, a disk of stars, gas, and dust with a central bar-shaped concentration of stars and elegant spiral arms wrapping outward. The disk measures about 100,000 light-years across and only about 1,000 light-years thick in most places, resembling 2 fried eggs placed back to back. Our solar system resides in the disk, about 26,000 light-years from the galactic center, in a minor spiral arm called the Orion Arm or Orion Spur. Because we're embedded in the disk, we see it edge on as the Milky Way band crossing our sky. When you look toward the constellations Sagittarius and Scorpius in summer, you're looking toward the galactic center, the heart of the galaxy. This direction shows the widest, brightest, most densely packed section of the Milky Way because you're peering through the maximum thickness of the galactic disk. When you look in the opposite direction toward Auriga and Taurus in winter, you're looking toward the outer edge of the galaxy, where the Milky Way appears narrower and fainter. The center of the Milky Way harbors a supermassive black hole called Sagittarius A star, with a mass approximately 4 million times that of the Sun. Despite this enormous mass, the black hole itself is relatively small, with an event horizon only about 17 times the diameter of the Sun. Around this central black hole, stars orbit in tight, fast trajectories. The star S2, one of the closest stars to Sagittarius A star, completes its orbit in only 16 years, reaching speeds of over 5,000 kilometers per second, more than 1.5% the speed of light. The Milky Way contains between 100 billion and 400 billion stars, with the uncertainty arising from difficulty counting the faintest stars and those hidden by dust. Recent estimates suggest about 250 billion stars is most likely. These stars range from red dwarfs with masses only about 8% that of the Sun to blue supergiants with masses exceeding 100 solar masses. The vast majority are faint red dwarfs, invisible to the naked eye, while the brilliant stars we see represent only the most luminous fraction of the stellar population. Most stars in the Milky Way orbit the galactic center in roughly circular paths, taking hundreds of millions of years to complete one orbit. Our Sun takes about 225 to 250 million years to orbit once, a period sometimes called a galactic year or cosmic year. Since the Sun formed about 4.5 billion years ago, it has completed roughly 18 to 20 orbits around the galaxy. Dinosaurs roamed Earth less than 1 galactic year ago. Complex multicellular life arose about 2.5 galactic years ago. The spiral arms visible in photographs of other galaxies are density waves, regions where stars and gas become temporarily compressed as they orbit. Stars drift in and out of these arms as they orbit, spending a small fraction of their time in the compressed regions where new star formation occurs. The bright, hot, young stars born in these regions give the spiral arms their luminous appearance. These massive stars burn bright and die young, often exploding as supernovae before they can drift far from their birthplaces, maintaining the spiral arm's bright appearance. Interstellar dust, tiny particles of carbon, silicates, and ices, blocks and scatters light, particularly blue light, creating dark lanes and patches visible against the background of stars. The Great Rift, a dark lane running through the brightest part of the Milky Way in Sagittarius and Cygnus, is caused by dust clouds blocking our view of more distant stars. Early observers didn't realize this, sometimes interpreting the dark patches as regions where few stars existed, but we now know they're simply obscured by intervening material. This dust also explains why optical telescopes can't see the very center of the galaxy. Looking toward Sagittarius, you can see the central bulge of the Milky Way, a roughly spherical concentration of old stars, but you can't see the true core. Infrared and radio telescopes can penetrate the dust, revealing the complex structure at the galactic center, including the supermassive black hole and the dense star clusters surrounding it. The Milky Way isn't alone in space, but rather leads a group of galaxies called the Local Group, containing more than 50 galaxies spread across about 10 million light-years. The three largest members are the Milky Way, Andromeda, and Triangulum. The rest are mostly dwarf galaxies, some containing only a few million stars, orbiting the larger galaxies or drifting through the space between them. Standing under the Milky Way, you're witnessing our cosmic address. Earth, Solar System, Orion Arm, Milky Way Galaxy, Local Group, Virgo Supercluster, Laniakea Supercluster, the Cosmic Web. Each level of this address represents a larger structure, each containing the previous ones, extending from our tiny planet to structures spanning hundreds of millions of light-years. The number of stars in the Milky Way is roughly comparable to the number of grains of sand on all the beaches of Earth. Yet the Milky Way is just one of hundreds of billions of galaxies. If every star in the Milky Way were a grain of sand, and you collected sand from every beach on Earth to represent every galaxy, you still wouldn't have enough sand to represent all the stars in the observable universe. The universe is vast beyond human comprehension, and standing under the Milky Way helps us appreciate, however inadequately, the scale of existence. Meteor showers and celestial events. The night sky isn't static. It changes throughout the night as Earth rotates, throughout the month as the moon cycles through its phases, throughout the year as Earth orbits the sun, and sometimes it changes suddenly and dramatically when meteors streak across the darkness. These transient events add an element of surprise and wonder to stargazing, reminding us that even the heavens are dynamic and active. Meteors, commonly called shooting stars or falling stars, are small pieces of space debris, typically no larger than a grain of sand, burning up as they enter Earth's atmosphere at speeds of 11 to 72 kilometers per second. The intense friction with atmospheric molecules heats the particle and the surrounding air to thousands of degrees, creating the bright streak of light we see. Most meteors burn up completely at altitudes of 80 to 120 kilometers, never reaching the ground. On any clear night, a patient observer can expect to see a few sporadic meteors per hour, random pieces of debris that happen to intersect Earth's orbit. But several times per year, the number of meteors increases dramatically during meteor showers, when Earth passes through dense streams of particles left behind by comets. Comets, sometimes called dirty snowballs, are composed of ice, dust, and rock. As a comet approaches the sun, solar radiation vaporizes its ices, releasing dust and gas that form the comet's spectacular tail. This debris continues orbiting the sun along the comet's path, spreading out over time to form a stream of particles. When Earth intersects one of these debris streams, the particles rain down into our atmosphere, creating a meteor shower. The Perseids, active in mid-August each year, are among the most popular meteor showers. They're caused by debris from comet Swift-Tuttle, which orbits the sun every 133 years. At its peak, the Perseid shower can produce 60 to 100 meteors per hour under ideal conditions. The meteors appear to radiate from a point in the constellation Perseus, hence the name, though they can appear anywhere in the sky. The Geminids in mid-December are another reliable shower, often producing rates of 120 meteors per hour or more. Unlike most showers, the Geminids come from an asteroid, 3200 Phaeton, rather than a comet. This asteroid may be an extinct comet that has lost all its volatile materials, or it may be a different type of object entirely. The Geminids are notable for producing bright meteors with medium speeds, making them spectacular to watch. The Leonids, peaking in mid-November, are usually modest, producing about 15 meteors per hour. But every 33 years or so, when the parent comet Tempel-Tuttle returns to the inner solar system, the Leonids can produce spectacular meteor storms with thousands of meteors per hour. The Leonid storm of 1833 was so intense that observers compared it to snowflakes falling from the sky, with estimates of hundreds of thousands of meteors during the peak hours. Similar storms occurred in 1866 and 1966, and a less intense but still impressive display occurred in 1999. Watching a meteor shower is one of the most peaceful forms of stargazing. You simply lie back, let your eyes adapt to the darkness, and watch the sky. No telescope is needed. In fact, telescopes are worse than useless for meteor observation because they restrict your field of view. The best equipment is your eyes, a comfortable reclining chair or blanket, warm clothing for cool nights, and patience. Each meteor appears for only a second or two, a brief flash of light tracing a line across the stars. Some are faint, barely visible like a distant spark. Others are brilliant, bright enough to cast shadows, sometimes leaving glowing trains that persist for seconds. Occasionally, a very bright meteor called a fireball will appear, brighter than any planet, crackling across the sky with visible colors, greens and oranges and whites. There's something meditative about watching for meteors. You can't predict exactly when or where each one will appear, so you must simply watch and wait, letting your attention rest gently on the sky. This creates a state of relaxed alertness, present in the moment but without straining or forcing. Thoughts drift away as you watch the stars, and when a meteor suddenly appears, it brings a moment of delight before you settle back into peaceful watching. Eclipses are among the most dramatic celestial events. Solar eclipses occur when the moon passes between Earth and the sun, blocking solar light. Lunar eclipses occur when Earth's shadow falls on the moon. Both types follow predictable cycles discovered by ancient astronomers. Total solar eclipses are rare for any given location, occurring roughly once every 375 years on average at any specific point on Earth. The path of totality, where the sun is completely covered, is typically only about 200 kilometers wide, and totality lasts only a few minutes at most. But along that narrow path, those few minutes are among the most spectacular experiences nature provides. As the moon gradually covers more and more of the sun, daylight dims almost imperceptibly at first. Then, as only a thin crescent of sun remains, the dimming accelerates. The temperature drops, animals behave strangely, birds falling silent, thinking night has come. Finally, the last bit of sun disappears and totality begins. The sky turns dark, stars and planets becoming visible in the middle of the day. Around the black disk of the moon, the sun's corona appears, a gossamer halo of pearly white light streaming outward, revealing structures and streamers invisible at any other time. During totality, you can look directly at the eclipsed sun without eye protection, seeing details impossible to observe otherwise. The prominences, loops, and sheets of glowing hydrogen rising from the sun's surface become visible as pinkish-red structures around the moon's edge. The experience is primal and profound, tapping into something deep in human consciousness that recognizes this as extraordinary, impossible, yet real. Lunar eclipses are more common and accessible, visible from anywhere on Earth's night side. As the moon enters Earth's shadow, it doesn't disappear completely, but instead turns a deep red or orange color. This happens because Earth's atmosphere bends and scatters sunlight, removing the blue wavelengths and allowing red light to reach the moon. The exact color depends on Earth's atmosphere at the time, particularly the amount of dust and clouds. After major volcanic eruptions, lunar eclipses can appear very dark, almost black, while at other times, they glow brilliant orange-red. Watching a lunar eclipse is peaceful and unhurried. The partial phases, when Earth's shadow gradually covers the moon, last over an hour. Totality can last over an hour as well, giving plenty of time to observe the color, the darkening and brightening of craters as they enter and exit the shadow, and the gradual emergence as the moon moves out of Earth's shadow. These events, meteors and eclipses, remind us that the sky is alive with motion and change. Earth travels through space at 30 kilometers per second, spinning on its axis. The moon orbits Earth, planets orbit the sun, and occasionally, these precise choreographed movements align to create moments of extraordinary beauty. We are privileged to witness these events, to know what causes them, and to predict when they will occur again. The dark sky and light pollution. One of the saddest developments of modern civilization is the loss of the dark night sky. For most of human history, every person on Earth could look up and see thousands of stars, the Milky Way, planets, and the grand display of the cosmos. Today, more than 1/3 of humanity cannot see the Milky Way from their homes due to light pollution. In North America and Europe, about 60 to 80% of people live under skies too bright to see our home galaxy. Light pollution is artificial light that illuminates the night sky, scattering off air molecules and particles in the atmosphere, creating a luminous dome over cities and towns. This wasted light, energy released upward rather than directed toward the ground where it's needed, drowns out the faint light from celestial objects. The brighter the sky background, the harder it is to see faint stars, nebulae, and galaxies. The darkest natural skies, measured on the Bortle Dark Sky Scale, are rated as Class 1, where the Milky Way is so bright it casts visible shadows, where zodiacal light and Gegenschein are easily visible, where thousands upon thousands of stars fill the sky. These conditions are now rare, existing only in the most remote locations. Deserts, mountains, remote islands, polar regions. Most suburban skies rate as Class 4 or 5, where the Milky Way is visible but washed out, where only the brightest nebulae can be seen, where a few hundred stars are visible rather than thousands. Urban skies rate as Class 8 or 9, where only the brightest stars and planets are visible, where the sky glows orange or gray from artificial light, where the Milky Way is completely invisible. This loss affects more than just astronomers. Many species of animals, from sea turtles to migrating birds to nocturnal insects, rely on natural darkness and celestial cues for navigation, reproduction, and feeding. Artificial light at night disrupts these behaviors, contributing to population declines in species already stressed by habitat loss and climate change. For humans, light pollution disrupts natural circadian rhythms. Exposure to bright artificial light at night suppresses melatonin production, interfering with sleep quality and timing. Communities with darker skies report better sleep quality on average. There's also growing evidence that chronic circadian disruption from light at night may contribute to health problems including obesity, depression, and certain cancers. The solution to light pollution is surprisingly simple. Use light only where and when needed, shield lights to direct them downward, and use appropriate wavelengths that minimize atmospheric scattering. Well-designed outdoor lighting can actually improve visibility while reducing light pollution and energy waste. Communities that implement dark sky-friendly lighting often find they save money on electricity while improving safety and aesthetics. The International Dark Sky Association recognizes dark sky parks and reserves, protected areas with exceptionally dark skies, and commitment to preserving those conditions. Visiting one of these locations is like stepping back in time, experiencing the sky as our ancestors saw it. The first moments under a truly dark sky are often overwhelming, as your eyes adjust and more stars appear, until the sky seems crowded with light. The Milky Way, a luminous river flowing overhead. If you live in an area with significant light pollution, you can still enjoy the night sky. Planets, bright stars, the moon, and meteor showers remain visible even from cities. But if possible, occasionally travel to darker locations. Drive away from city lights, visit a dark sky park, go camping in remote areas. Experience the sky in its full glory at least once. The memory will stay with you, a reminder of the vast cosmos we inhabit, hidden above us even when we can't see it. The movement to preserve dark skies is gaining momentum. More communities are adopting dark sky-friendly lighting ordinances. More parks and reserves are being designated. Awareness of light pollution is growing. There's hope that future generations might recover some of what we've lost, that the stars might return to more of the world's skies. Until then, cherish whatever stars you can see. Even a few stars, even just the moon and planets, can provide a connection to the cosmos. And remember that above the glow of artificial lights, the universe continues unchanged, billions of galaxies spanning billions of light years, waiting patiently for when we look up again. Cosmic timescales and the eternal night. When you look up at the night sky, you're witnessing something so ancient, so deeply woven into the fabric of time itself, that it's almost impossible for the human mind to grasp. Every photon of starlight that touches your eye has been traveling for years, decades, centuries, sometimes millions of years before finally reaching you on this particular night, in this particular moment of your life. The darkness between those points of light isn't empty. It's filled with time, with distance, with the vast gulfs that separate one burning star from another across the cosmic ocean. Our universe began approximately 13.8 billion years ago in an event we call the Big Bang, though that name hardly does justice to what actually happened. It wasn't an explosion in space. It was the birth of space itself, the beginning of time as we understand it. In those first fractions of a second, everything that would ever exist was compressed into a point smaller than an atom, hotter than anything we can truly comprehend. And then it expanded, cooling as it grew, allowing the first particles to form, then atoms, then eventually, after hundreds of millions of years of darkness, the very first stars began to ignite. Those earliest stars were different from the ones we see today. They were made purely of hydrogen and helium, the simplest elements, forged in the crucible of the Big Bang itself. They burned bright and fierce and short-lived, many of them exploding as supernovae after only a few million years. But in their deaths, they scattered heavier elements throughout space, carbon and oxygen, iron and gold, all the ingredients necessary for planets, for oceans, for life. Every atom in your body except for hydrogen was made inside a star. You are, quite literally, composed of ancient starlight, the remnants of suns that died billions of years before Earth even existed. The night sky you see now is populated by stars of every age and type. Some are young, just a few million years old, still hot and blue and blazing with the fierce energy of youth. Others are middle-aged like our own sun, which has been burning steadily for about 4.6 billion years and has roughly another 5 billion years ahead of it. But the most fascinating stars, at least when we're thinking about time on truly cosmic scales, are the red dwarfs. Red dwarfs are the smallest, coolest stars capable of sustaining nuclear fusion. They're so faint that not a single one is visible to the naked eye, even though they make up about 75% of all stars in the galaxy. The closest star to our Sun, Proxima Centauri, is a red dwarf, sitting just over 4 light-years away, and yet we can't see it without a telescope. These humble, secretive stars burn their hydrogen fuel so slowly, so carefully, that they can continue shining for timescales that make the current age of the universe seem like nothing more than a brief opening chapter. A red dwarf with about 1/10 the mass of the Sun can burn for nearly 6 trillion years. Some of the smallest red dwarfs might last even twice that long. Think about that for a moment. The universe itself is only 13.8 billion years old. That means these stars, which have been around since nearly the beginning, have barely used even 1% of their fuel. They're still in their infancy, cosmically speaking. They'll be here long after our Sun has died, long after the Milky Way has merged with Andromeda, long after most of the gas in the universe has been used up and no new stars can form. The secret to their longevity lies in how they move their fuel around. Larger stars like the Sun have a core where fusion happens, surrounded by layers where energy slowly radiates outward. Only about 10% of the Sun's hydrogen ever gets used, because the hydrogen in the outer layers never makes it to the core. But red dwarfs are different. They're completely convective, meaning their entire interior churns and mixes like a pot of boiling water. Fresh hydrogen constantly gets cycled down to the core where it can be fused, and the helium produced gets mixed throughout the star. This means a red dwarf can use nearly all of its hydrogen, making it extraordinarily efficient. Imagine standing on a planet orbiting one of these red dwarf stars, one that formed shortly after the Big Bang. You'd be bathed in a dim, reddish light, cooler and darker than sunlight, but steady. And that light would continue, unchanging, for trillions upon trillions of years. Entire civilizations could rise and fall. Species could evolve, build vast technologies, forget them, evolve again. The star would barely change. It would be a constant, a beacon in the darkness that would outlast almost everything else in the cosmos. But even red dwarfs don't burn forever. Eventually, after those trillions of years, they'll exhaust their hydrogen. When that happens, something interesting occurs. Instead of swelling up into a red giant like the Sun will, a red dwarf will actually get hotter and bluer as it contracts. It becomes what astronomers call a blue dwarf, a hypothetical stellar phase that the universe isn't old enough to have produced yet. The blue dwarf stage might last another 5 billion years or so, and then finally the star will cool and fade, becoming a white dwarf. White dwarfs are the corpses of stars, dense balls of degenerate matter about the size of Earth but containing the mass of the Sun. They're hot when they first form, sometimes hundreds of thousands of degrees, but they're no longer generating energy through fusion. They're just glowing from leftover heat, slowly radiating it away into space. The oldest white dwarfs in our galaxy today, which formed from stars that died billions of years ago, have cooled down to about 4,000 degrees Celsius. They glow a dull red, like an ember in a dying fire. But 4,000 degrees is still scorching hot compared to where they're headed. Given enough time, measured not in billions but in quadrillions of years, these white dwarfs will cool all the way down to near absolute zero. They'll stop emitting visible light entirely. They'll become black dwarfs, dark and cold and utterly silent, drifting through space like tombstones marking the graves of ancient suns. The universe isn't old enough yet for any black dwarfs to exist. Every white dwarf out there is still radiating at least a little bit of heat. But someday, in a future so distant that the numbers become almost meaningless, the cosmos will be full of these cold, dark remnants. And here's where things get truly strange. Even black dwarfs, even these frozen stellar corpses, may have one final act to perform. Deep inside a black dwarf, atomic nuclei are packed incredibly close together. At such cold temperatures, nothing much happens. The laws of thermodynamics seem to have won, and the star is truly dead. But quantum mechanics, that strange set of rules governing the smallest scales of reality, says that particles can occasionally do something called quantum tunneling. They can suddenly jump across barriers they shouldn't be able to cross. And if two atomic nuclei tunnel close enough together inside a black dwarf, they can fuse very slowly, atom by atom, releasing tiny amounts of energy. Over unimaginable timescales, this process, called pycnonuclear fusion, will gradually convert the material inside black dwarfs into iron. Iron is the most stable element, the end of the line for fusion. You can't get energy from fusing iron. It's the cosmic dead end. But as more and more of a black dwarf's interior turns to iron, something critical happens. The star gets denser, heavier, and there's a limit to how much mass a degenerate object like a white dwarf or black dwarf can hold. This limit, called the Chandrasekhar limit, is about 1.4 times the mass of the Sun. If a white dwarf exceeds this mass, usually by pulling matter from a companion star, it collapses and explodes in what we call a Type 1 supernova. But black dwarfs don't have companion stars in this far future. They're alone in a cold, dark universe. Yet as iron accumulates in their cores, the most massive black dwarfs, those with about 1.2 to 1.4 solar masses, will eventually reach a tipping point. Physicist Matthew Kaplan calculated when this might happen. His work suggests that the first black dwarf supernova could occur in about 10 to the power of 1100 years. That's a 1 followed by 1100 zeros. To put that in perspective, the current age of the universe is only about 10 to the 13th power years, which is a 1 followed by 13 zeros. We're talking about a time span so vast that it's literally beyond human comprehension. By the time the first black dwarf explodes, the universe will have been cold and dark for so long that this time, right now, will be forgotten, unimaginable, lost to eternity. These black dwarf supernovae will continue, gradually, as less and less massive black dwarfs accumulate enough iron in their cores to collapse. The last one might occur around 10 to the power of 32,000 years from now. After that, if these calculations are correct, the universe will have experienced its final supernova, its last explosion, the last significant release of energy in all of existence. And then, truly, it will be dark. What does darkness mean on such scales? It's not the comfortable darkness of night, where you know the sun will rise again in a few hours. It's not even the darkness between the stars, where if you look closely enough, you can always find another pinpoint of light. This is the darkness of a universe that has run down completely, where every star has died, every black hole has evaporated through Hawking radiation, a process that takes 10 to the power of 100 years, and every possible source of light and warmth has been exhausted. In this far future, space will be filled with dark, cold objects. Black dwarfs, neutron stars, the occasional wandering planet ejected from its orbit billions of years earlier. The temperature will be just a fraction of a degree above absolute zero, matching the faint afterglow of the Big Bang itself, which will have stretched and cooled into almost nothing. There will be no observers, no life, no one to witness the profound silence. And yet, in a strange way, this future universe will still contain everything that ever existed. All the atoms that made up every star, every planet, every living thing, they'll still be out there, just rearranged, cooled, separated by distances so vast that they might as well be alone in separate universes. The light from stars that once shone will still be traveling, stretched into radio waves so long and faint they're essentially undetectable, propagating outward forever into the expanding darkness. Some physicists speculate about what might happen even further beyond this point. If protons are not stable, if they eventually decay, then even the atoms that make up black dwarfs and planets will fall apart, leaving nothing but a thin soup of electrons, positrons, neutrinos, and photons, all of them redshifted to nearly zero energy. The universe would become something so dilute, so empty, that the concept of matter itself loses meaning. Other theories suggest different endings. Perhaps the expansion of the universe will accelerate so much that space itself begins to tear apart, ripping atoms, then nuclei, then even fundamental particles into oblivion in what's called the Big Rip. Or perhaps, in a closed universe, gravity will eventually win, and everything will collapse back into a big crunch, possibly giving birth to a new universe in an endless cycle of creation and destruction. But all of these possibilities, whether heat death or Big Rip or Big Crunch, they all share one common thread. The night will come, the eternal night, the final darkness. And unlike the night we know, which is temporary, cyclical, relieved by the rising sun, this darkness will be permanent. There will be no morning. When you look at the night sky tonight, you're seeing the universe in its prime, in its age of stars, when galaxies are still bright and new stars are still being born in stellar nurseries, when planets orbit in habitable zones and life might be emerging on countless worlds we'll never know about. This is the golden age of the cosmos, and we're privileged to be alive during it. In the grand scheme of cosmic time, we're living in the very beginning, in the brief, brilliant flash when the universe is young and full of light. The darkness between the stars that you see isn't really darkness. It's just distance and time. Those gaps are filled with the history of light, with photons on their journey from distant suns. When you trace a line from your eye to a star, you're connecting across light years, sometimes across centuries, touching something ancient with your gaze. That star might be dead already, its light still traveling toward us, a ghost beam from a sun that no longer exists. Betelgeuse, the red supergiant star in Orion's shoulder, is about 640 light-years away. That means the light you see left that star in the 1400s, around the time of the Renaissance on Earth. If Betelgeuse exploded in a supernova today, we wouldn't know for more than 6 centuries. The night sky would look the same to us, unchanging, until suddenly, one night, a new light would appear, bright enough to see during the day, a messenger from the distant past finally arriving to announce what happened long ago. This is what the night sky is, a window into history, a map of time as much as space. The farther out you look, the farther back you see. The most distant galaxies visible to the James Webb Space Telescope are so far away that their light has been traveling for over 13 billion years. We see them as they were when the universe was less than 1 billion years old, shortly after the first stars formed. Those galaxies don't look like that anymore. They've evolved, merged with other galaxies, formed new stars, perhaps even been home to civilizations that looked up at their own night skies and wondered the same questions we wonder. And someday, in that distant future we've been contemplating, when the last stars have died and the universe has cooled into darkness, there won't be any night sky to look at. There won't be anyone to look. The photons from ancient stars will still be out there, still traveling, but they'll be stretched by the expansion of space into wavelengths so long they carry almost no energy. The universe will be dark not because light doesn't exist, but because it's become invisible, transformed by time and distance into something that can no longer be seen. The night sky is a gift, a reminder of our place in something vast and ancient and beautiful. It's easy to forget this when we live in cities where light pollution washes out the stars, where we can see only a handful of the brightest points and miss the river of the Milky Way that should arc overhead. But if you can find a dark place, away from the glow of streetlights and buildings, and give your eyes time to adjust, you'll see what our ancestors saw, what every human culture in history has looked up at and wondered about. You'll see thousands of stars, each one a sun, many of them with planets of their own. You'll see the cloudy band of the Milky Way, which is our galaxy seen edge-on, billions of stars too distant and faint to resolve individually but collectively creating that soft, glowing path across the heavens. If you're in the southern hemisphere, you might see the Magellanic Clouds, small companion galaxies to our own. If you look toward Andromeda with even a small telescope or binoculars, you can see the faint smudge of the Andromeda Galaxy, the light from 1 trillion stars over 2.5 million light-years away. Every one of those photons traveled through space for millions of years just to reach your eye. You're not just seeing the Andromeda Galaxy. You're seeing it as it was 2.5 million years ago, long before humans existed in their current form, when our ancestors were still using simple stone tools. That galaxy has been slowly moving toward us, and in about 4 billion years it will collide with the Milky Way, merging into a larger galaxy. Our night sky will be transformed, filled with new stars, new constellations, a display of cosmic fireworks as two galaxies dance together and become one. But you'll never see that. Neither will your children or their children or thousands of generations yet unborn. It's too far in the future, too distant in time. What you can see, what you have right now, is this moment, this night sky, these stars and these patterns shining down on this particular version of Earth. It won't last forever. The stars themselves are moving, slowly shifting position over thousands of years. The constellations we know, the patterns we've named and told stories about, they're temporary. In 100,000 years, Orion won't look like a hunter anymore. The Big Dipper will have stretched and warped into a shape our descendants won't recognize. Everything is temporary, except perhaps the darkness itself. The gaps between the stars will always be there, growing wider as the universe expands, until eventually each galaxy is alone in an island universe, too far from any other to see. And then, as we've discussed, the stars will die one by one until only darkness remains. But that's not cause for sadness. It's cause for appreciation. We're here in the age of stars, in the time when the universe is bright and full of possibility. We have the privilege of looking up and seeing light, of knowing that somewhere out there, around some of those distant suns, there might be other beings looking back, wondering the same things we wonder, feeling the same sense of smallness and significance that comes from contemplating the cosmos. So take some time tonight, if you can, to look up. Let the night sky remind you of deep time, of the billions of years that came before and the trillions that might come after. Let it remind you that you're part of something ancient and ongoing, that the atoms in your body were forged in stars, that you're made of the universe looking back at itself, briefly conscious, briefly aware, a way for the cosmos to know itself. If you enjoyed this journey through cosmic time and the eternal night, please give this video a like and subscribe to Deep Science Sleep for more sleepy science stories that explore the wonders of the universe. Share your thoughts in the comments below about what the night sky means to you, or what cosmic topics you'd like us to cover in future episodes. Until next time, sleep well under the stars, and remember, even in the darkest night, you're surrounded by light that's been traveling across space and time just to reach you. Sweet dreams and clear skies.